Good afternoon. This is Prof. Bill speaking to you from a land very far away. And today we are going to start talking about Chapter 10, Graphs and Trees. Here it is right in your book. This is the last section that we'll be covering in this class. I think it's a very interesting chapter, and I hope you enjoy it as much as I do. So let me get my screen set up for you, and I will start describing some stuff for you. So we're talking about graphs today, and we have to give some definitions of it. So these are graphs. These things are going to seem a little bit strange at first because there's not a whole lot to them. I'm going to draw some dots over here like this. And then what happens is I'm going to give these dots names, and I'll call that one A, B, C, D, E, and F. And I'll draw some lines between them. So there's a line, and there's a line, and there's a line, and there's a line. And believe it or not, what we have here is this is an example of what's called, this is an example of an undirected graph. And we have to give lots of definitions here. And we're going to call this an undirected graph, and we're going to call it G. And according to your book, there are a couple of things we need to define here. Now, first of all, notice that we've got these dots here. Okay, so these dots, what I'm calling dots, there are a couple of other names for them. We might refer to them as nodes. The other word that we might see here is each one of them is called a vertex. And the plural of vertex is vertices. Okay, so that's plural. And what your book would say is your book would say that we would have a set there called E of G. And this is equal to, I'm sorry, that's not E of G. That is V of G. And that's equal to the vertex set. Actually, I like to just call it plain old V. And I would say that V is equal to A, B, C, D, E, and F. Just like that. Okay, so those are the vertexes. And then the other thing is what is called E of G. And I just like to call that E. And that is the edge set. Now what we have to do here is we have to have a way of specifying what an edge is. And what we can do is we can specify the edges by the endpoints of the edges. So for example, here is an edge that goes between the vertex A and the vertex E. So that could be written this way as the set AE. Now you may remember back when we talked about sets, remember that the set AE is the same thing as the set EA. So we're going to make sure that when we give the edge set, we don't want to repeat these things over here. But in this edge set over here, we can see that there's AE, there's FD, so that's EA, there's FD, there's DC, okay, and then there's also BC. So there's 1, 2, 3, 4 edges. Let's make sure I got them all. Here's 1, here's 2, here's 3, here's 4. And this is the edge set. It's equal to this set of sets. Okay? So what we do when we're talking about defining undirected graphs, very frequently in the literature, you'll see something like this. You'll see that a graph G is equal to, and they'll use ordered set notation here. They'll say V and E, where V is your vertex set, and that looks just like this over here. And then E is your edge set, which looks just like this over here. Okay, and what's important here is this is what's called an undirected graph. Now what I want to show you is I want to show you something called a directed graph. Okay, so this is going to be directed graph. And in a directed graph, again, we have a set of vertices. So here we'll have A, B, C, D, E, and F. But now what happens is the edges actually have a direction on them. So you can think of these as like being one-way streets. And what I do is I put arrows to indicate that I'm going from A to B. So I want you to distinguish this from the undirected graph. In an undirected graph, we're basically saying that you can go in either direction here. You can go from B to C, or you can go from C to B. But over here in the directed graph, there is a direction associated with it. So let's come over here and let's do this. And let's come over here and do that. And do this. There's nothing particularly important about this graph. I'm just making these things up for example. So we've got one that goes there. And you could certainly have one that comes back. So here's one. It's going back that way. I hope that's clear. So anyway, again here, the notation here is going to be a little bit different. Now, the vertex set is still going to look the same. So here it's going to be A, B, C, D, E, F. But now when it comes to specifying the edges, I'm going to be doing things a little bit differently. Now, you may recall back here, we said that in specifying the edges, we just gave a set. And remember, in a set, AE is the same thing as EA. And again, that really captures the fact that there's no beginning or end point here. You could start in one and go to the other. But over here in the directed set, it makes a big difference because the edges now have a direction on them. So what we're going to do here is we're going to use ordered pairs to specify an edge. So for example, if I want to talk about this edge from A to C, instead of using the set bracket, I'm going to use the ordered pair bracket, A, C. And notice that AC, this is not the same thing as CA. Okay, this is an ordered pair. So the order of these things is very important. So when I come over here and I specify the sets of these, okay, well there's a set AB. And then there is AC. And then there is BF. And then there is FE. And let's see, from here, notice there is ED and then there's DE. So I have to specify those separately. So I've got ED, comma, and then I've got DE. And then I close up the set. Okay, so here, this is a directed graph. And again, notice that we're using ordered pairs here. This is an undirected graph, so notice that down here, we're just using the set notation. Okay, Let's restrict ourselves to the moment to undirected graphs. And let's come over here and let's draw a very simple one. So here's A, B, C, D. And let's make it look like a box. Okay. Now, I want to define something here. It's called adjacency. And I'll try to give it another number here. I'm going to call it neighbor. Okay, and let's pick a point here. I want to pick this point B, and I want to talk about what is the neighborhood of B. And I'm going to call that N of B. And it turns out that N of B here, well, I want to talk about all of the points, okay, all of the vertices that are adjacent to it. In other words, where I'm connected to it. So in this case, N of B is equal to the set A and C. And likewise, if I want to come along here, I can compute these other neighborhoods, if you will. So the neighborhood of A would be B and D. And the neighborhood of C would be D and B. B and D. And the neighborhood of D would be A and C. Okay. Now, when it comes to drawing graphs, there are a couple of things that don't matter. Okay. For example, if I were to look at this graph right over here, and I were to look at this graph right over here, and I'm making the edges longer, and instead of calling it A, B, C, and D, I called it Doug and Bill and Sue and Mary. To somebody studying graph theory, these two graphs are exactly the same thing. And the reason why they're the same thing, well, first of all, we can see they look the same. The fact that these edges are longer, that means nothing to somebody studying graphs. But the other thing is that I could actually have a function from points to points that maintains the neighbors. In other words, I could come over here and I'm going to say something like the following. I'm going to say let f of A equal Doug. And I'm going to say let f of B equal Bill. And I'm going to say let f of C equal Sue. And I'm going to say let f of D equal Mary. And what I am suggesting to you is that this function here is going to maintain the notion of adjacency. In other words, over here, notice that I said that f of A is Doug, and notice that the neighbors of A are B and D. Okay, well, that would say over here that the neighbors of Doug should be whatever f of B and f of D are. Well, f of B is Bill, and f of D is Mary. Okay, and we can see that what's happened here is just like this has come down to here, the neighbors have maintained the same. So what this function has done here, this function here has maintained the notion of neighborhood. Okay, this maintains neighbors. And the point is that if I can have a function from one graph to another that maintains the neighbors, as far as a graph theorist is concerned, we would say that these are absolutely the same graph. Now let me give you another example where it may be a little bit less obvious. Suppose I came over here and I had a graph that looked like this. Okay. So I want to consider that with another graph right here. It looks like the following. Whoops, teacher made a mistake. I want to consider that with a graph that looks like this. Okay, and I'm going to call this A, B, C, D, and E. Now, I claim that these two graphs are exactly the same. And watch what's going to happen. I'm going to say, well, I want to map A over to this point here, and I'm going to call it A prime. And I'm going to go, well, A has neighbors B and E. So the neighbors of this, I'm going to call this B prime. And the other neighbor is E, so I'm going to come over here, and I'm going to call this E prime. And then I notice, well, B has neighbors A and C, so here's B's neighbors. B prime's neighbors are A, so this one over here would be C prime. Okay, and then let's see, E prime's neighbors are A and D. Well, E prime is A, so this must be D prime. So what I am suggesting to you is that this mapping from any point X over to some point X prime, given this labeling here, is going to maintain neighbors. So the conclusion here is that these two graphs are exactly the same thing. They maintain the neighborhoods, all right? This is a fairly easy example, and in general, it's not easy to tell if two graphs are the same. There are certain things that you can look for that will tell you that they're not the same. For example, if I came over here and suppose I drew a graph that looked like this, and over here I drew a graph that looked like this, the same one that we have over there as before, now I know that these two graphs aren't the same, and I can tell you why very quickly. Notice that this point here has two neighbors. And notice that this point here has two neighbors, but this point down here has three neighbors. 1, 2, 3. Likewise, this point over here has three neighbors. 1, 2, 3. But if I come over here, all 5 points have two neighbors. So there is no way that these two can be the same. Okay? So one way that I can tell that two graphs aren't the same is as if I look at the points and they have different numbers of neighbors. By the way, in this example over here, there's a big word to learn here, and the word is called isomorphic. Okay? And the tough part here is if you want to show that two graphs are isomorphic, what you need to do is you need to find a function from points to points that maintains the neighbors. Now that's not necessarily so easy to do, okay? I want you to think about this for a second. Over here I have 5 points, and over here I have 5 points. And the question is how many functions can I come up with from 5 points to 5 points? Well, you should know the answer to that from a previous chapter. I can send the first point to any one of 5 points, and then I can send the second point to any one of the 4 remaining points, and then I can send the third one to any of the 3 remaining points, so that the number of different functions would be 5 factorial. 5 times 4 times 3 times 2 times 1. Well, for the number 5, that's not too big a number. Let's see, what is that? 20, that's 60, that's equal to 120. But that means that if I'm trying to show that these two graphs are isomorphic, I in theory have 120 different functions that I'm going to have to try and hope that one of them maintains the neighbors. If I go through all 120 of them and the neighbors aren't maintained in any of them, then they are not isomorphic. On the other hand, it's much easier to look over here and I can argue these can't be isomorphic because I have points over here that all of these points here only have 2 neighbors, whereas I've got 2 points over here that have 3 neighbors. This is a very important point. So please think about it before you continue. All right, here we go again, folks. Some more definitions. Sorry about that. I know definitions aren't always fun. These aren't bad. So again, let's come over here and let's make up a graph. So here's a point, here's a point, here's a point. Let's do that. Let's do this. So let's call this A, B, C, D, E, F, and G. Okay, now that's a graph. Okay, we've got our vertices, we've got our edges. Sometimes you will find that people find it convenient. Instead of referring to an edge here as the set AB, maybe they'll stick a label on it, and they'll call this E sub 1. And they'll call this E sub 2, E sub 3, E sub 4, E sub 5. So we've got 5 edges here, okay? So for example, E1 is just equal to the set AB, okay? Or E2 is equal to the set BC. Okay, that's pretty easy. Okay, so the first thing that we want to note is we want to talk about something that's called a path. Okay, and a path is it's a sequence of edges. So and I'm going to make this really informal, that are connected from end to end. Okay, we don't really need to be that formal here. But for example, over here, I want you to notice here that we have a path. I'll give an example of a path. So here's a path, E1, E2, E3. Okay, it's a path, okay, like that. Not a path. E1, E3, okay? Because these guys aren't connected head to tail, okay? So here's a path, like here, E1, E2, E3. Here's a path, E1, E2, E5. And I think you get the idea. Okay, so that's the first definition you should know. You should recognize what a path is. The next thing that we can talk about here is what is called a connected graph. And yes, this is a definition. A graph G is connected if and only if there is a path between any pair of vertices. Okay, so if this is a graph up here, G, if I were to say to you, is this connected? The answer is no. There is no path from A to G. Okay, just to give you another example, we could have a graph that looks like this. Here's G. Okay, and it's made up of these 1, 2, 3, 4, 5, 6, 7 points. Okay, and clearly it's not connected because there is no way to get from this point here to this point here. So this is not connected. Okay. Another definition here, a cycle. A cycle is a path that ends where it begins. Again, this is, I'm going to say this is informal. Okay, so for example, here's a graph G. And I say to you, is there a cycle in this graph? And the answer is yes. Right here, I can see that there's a cycle. There's a path that takes me right back to where I begin. Okay. Another definition. A tree this is a definition. A tree is any connected graph without a cycle. So here's an example of a tree. That's a tree, okay, because it is connected, okay, and we can also see that there are no cycles here. So that's a very good definition to keep in mind. And later on in this chapter, we're going to be looking at trees. You've probably seen trees in some of your other classes. Maybe you studied things called binary search trees that sort of look like this. And there are lots of interesting properties of trees, and we will be discussing them. Okay, a couple of more definitions here. Okay, and what I want to do here is I want to discuss, I'm going to call these famous graphs. So the first one is, I'm going to call this the complete graph. On n vertices. And this is denoted in the book, as well as in the literature, as K subscript n. And what this means is that every vertex is connected to every other vertex. Okay, so for example, let's look at some of these. Here's K2. So K2, I just do that, and I do that, and it looks like that. And here is K3, and that would be 1, 2, 3, and I go like that. K4, 1, 2, 3, 4, and let's see, I have to connect this one to here, and I have to connect it to here, and I have to connect it to here. Now this one has to come down here, this one has to also go over here, and down there, and now I come over here, and now everyone is connected to everyone else here. So that's K4. Here's K5. 1, 2, 3, 4, 5. So I want you to notice something because we're going to come up with a theorem in a second. There are 5 points here. So if I'm over here, I have to connect this to 4 other points. So I've had to connect this one to 4 points. Now I have to go to this one over here. Well, this one's already connected here, so there are 3 remaining points to connect this one to. So that's 1, 2, 3. And now I have to come over here. So this connected to 4 points. This one was going to connect to 3. This one still has 2 remaining points to connect to. So there's 1. And there's 2. And now when I come over here, this only has 1 left. So if the question was for K5, how many edges are there? Well, there are 4 plus 3 plus 2 plus 1. That's equal to 10. So if I would say to you, how many edges in K6? Well, that's going to equal to 5 plus 4 plus 3 plus 2 plus 1. And here's the theorem. Kn has n minus 1 plus n minus 2 plus 2 plus 1 edges, and we should have a formula for this, and we do have a formula for that, and it's n times n minus 1 2 edges. And yes, that is a very good fact for you all to know. All right. One more famous graph. This is called a bipartite graph. And it has 2 parameters. And you write this K, M, comma, N, like that. Okay. Before I show you the general one of this, let me show you a problem. This is a problem we have here in the United States, maybe less so in Namibia. Okay. But I want you to imagine that I've got a house here. So there's a house, and here's a house, and here's a house. Okay, and I also want you to imagine that we have 3 different utilities. So here's water. I'll put a W around it. And here's the electric company, so that we can watch TV and get on the internet. And then, I don't know if you have this in Namibia, but over here we also have the gas company. And the reason why we have the gas company is because we use gas to heat our homes, which get very cold in the winter. So we have 3 utilities and we have 3 houses. Okay, so again, you should be thinking a graph. Okay, there are 6 edges or 6 vertices here. And the question is, can I run lines from each utility to each house without them crossing? So for example, I go from this house to this one, and I go from this house over to this one, and then I go from this house over to this one. And so far it's so good. Now for this house, I might say, okay, let's come around here, and let's do that. And now for this one, let's come around here, and let's do that. And now for this one over here, let's come over here and do that. And now for this one, all right, go to the gas company, you come around here to go to the electric company, and I hope you all see that I now have a problem. And I'm going to go, where does that go? Okay. And it turns out, and we're not going to prove this, it turns out that this can't be solved. There is no way that I can do these in the plane like this without them crossing. Of course, if I go into 3 dimensions, I could dig under other tunnels and do stuff like that. But anyway, this graph that I have right here, if I have a set here with 3 elements in it, and I have another set here with 3 elements in it, and basically I draw from all of one set to all of the other set, like that, and then I come over here, and I don't care if they cross, but I do this, and then I do that, and then I do that, and then I come over here, and I do this, and I do that, and I do that. This right over here is the graph, the bipartite graph 3, 3. In other words, I have a set of 3 vertices over here, and I have a set of 3 vertices over here, and I consider them as separate sets. And what I do is I connect every one in one set to all the other ones in the other set. So for example, if I wanted to come over here, and I wanted to have K 2, 4, so I would put 1, 2, 3, 4 on one side, and I would put 2 on the other, and I might do something like this. This is what the graph would look like. So there's K 2, 4. So the question is how many edges? And the answer would just be m times n. I hope that's clear. These are very interesting graphs, and people have studied these quite a bit. And there are a lot of interesting applications for this. For example, you could think of this as being something like the following. Maybe these represent people, and maybe these represent items for sale in a store. Or maybe these represent people, and maybe these represent books that they've read. Okay, now nobody says that we have to make all the connections like that. It could be some subgraph of that. Maybe I've read this book, and I've read this book, and I've read that book, and maybe you've read this book, and this book. So this would be called a subgraph of K 2, 4. But people are doing a lot of analysis on these graphs in social network theory. Okay, part of this goes on maybe if you're doing shopping online, and maybe what we're doing is we're trying to find, are there other people out there that have similar shopping habits to what you have? You get that by studying these things called bipartite graphs. And I think this might be a good place to stop.